Okay, so let's start the class. I am Ayan from IIT Kanpur, and I am doing my PhD here on atomic physics, cold atom. So I'll teach you the time-independent perturbation theory. This portion that is a part of your advanced quantum mechanics course. Okay, that is in your semester 7. And I think, and one thing I want to mention, that in your next semester I think you have to choose between project and some course. Okay, I'll suggest you to take the project if you are allowed to take and if you want, because that will helpful a much when you apply for PhD in outside India, and you will learn something new. Okay, and you will learn more than doing any course. So that is very helpful. So try to take one project. Okay, let's come to the syllabus. So in the time independent perturbation theory, there are, first of course we will learn what is the perturbation theory, why we need it. Okay, then what in the syllabus there are, we for we have to do the correction of first order and second order correction to the energy eigenvalues of any system. Okay, and then we have to do the first order correction to the energy eigenvector or energy eigenfunction. This two part we have to do first, and why up to second order of the correction and why not in the second order in the correction in the wave function or wave vector, not in the higher order. At this stage for our problem, the second order correction in the energy and the first order correction in the wave function or wave vector, that is enough. That's why we will stick up to this. For further calculation, for more precise result, we have to go to the higher order correction. Okay. And then we will analyze that the this theory, perturbation theory, whether that is a converging theory or a diverging theory, because the energy of a system, that is a finite number. Okay, so the this first order, second order correction that we are doing to the energy, and of course a zeroth order, that means that is the only the solution of the Schrodinger equation. Putting all these three, that should be a finite number, that should not diverge. Okay, so there we will see the convergence of the non-degenerate perturbation theory. Non-degenerate comes from when the system has no degeneracy, and then we will move towards the degenerate perturbation theory, because we know the in the most cases the system are degenerate, like hydrogen atom system, 2D and 3D potential well, or any 3D harmonic oscillator. Okay, all these are degenerate theory, so we have to also develop a degenerate perturbation theory, and then we will apply this degenerate perturbation theory to the one electron system, like hydrogen atom system or hydrogen like system. Okay, there we will study the Stark effect, that is the effect of electric field on an atom. If we place a atom in an electric field, then how the energy levels of that atom changes. Okay, how the energy eigen function or eigenvector that changes, that will be analyzed under this star effect. Yeah, mm, that is called the star effect. And for the non-degenerate perturbation theory also, we'll solve many problems, and I will also give you problems that you have to solve. You have to solve, and I think in this portion the main problem is, like, in the syllabus it is just mention this name of the topics. Okay, so non-degenerate perturbation theory or degenerate perturbation theory. In the non-degenerate perturbation theory there are many examples, many. Okay, so I will so the main goal of this course will be that I will teach you the theory part. Okay, and of course you have to make a strong base, so that in exam if a unknown problem is given, you can solve it by the formulas. Okay, That is the main goal of this course, because there is no limit of doing problems. Okay, so for this course, I will mainly follow this David J. Griffith, this book. This is good book for as a textbook. Okay, first read this Griffith. Okay, and then go for the Sakurai. Okay, so the main at first read the quantum mechanics by David J. Griffith, and then move to Sakurai book, because in Sakurai book you will find the elaborate examples and elaborate theory of the this perturbation theory. There is more physical examples, and you can also go through this Brunson and Joachim this book. These three books are required for this portion. Now move to what is the perturbation here for this quantum mechanical system. What is the perturbation we are talking about? Um, can you answer anything? Do you have any idea about it? Okay, so as Sayonika said that in perturbation, what do we do? We use a small disturbance in the system. Okay, so this is a like what do you talk about the small? Okay, there is, if you don't compare with any other thing, then there is no concept of small or big. Okay, so that's why we have to talk about relatively small. Okay, relatively small potential. If we add a relatively small potential to our unpart of Hamiltonian, okay, then we'll call the new potential that we included, that is the perturbation Hamiltonian. Okay, so here I used the potential term loosely, because like in the perturbation, it is not necessary that in this V that should only be as a function of r. Okay, the Porter Hamiltonian, that the new that we want to add, that can also be as a function of p. Okay, function of kinetic energy, that is also valid. So in perturbation theory, what do we do? We introduce a relatively small potential or relatively small disturbance in the Hamiltonian, and for one system, maybe this VR, in one system it is relatively small, but in the other system, this VR may become big. Okay, large. So all the time we have to compare with the unpart of energy. Okay, if this VR, if M and N, uh, if the expectation value of this part of Hamiltonian, if it is very small than the En 0. Okay, like value of the unpart of Hamiltonian that is solved by the Schrodinger equation. If this is very small to the unpart of energy, then we will call it relatively small. Okay, let's get some example. And if you talk about why we need this kind of theory, what is the necessity? We have the Schrodinger equation. So what is the necessity of the new formulation? For all many times we cannot solve our system analytically. Okay, like when we solve the if you take the diatomic molecule system, the molecule individual atom with small m mass and capital M mass, if we want to analyze the motion or the interaction between them, that is in general it is a asymptotic potential. Okay, it is like something like that. Okay, but what we did at the first place, we took a quadratic approximation at the minimum point. the potential looks like a it varies as x square function. Okay, so we took this portion, okay, this small portion as our potential. Okay, so we solve at the first place we solve for this portion, but if we go from a large x, okay, then it is a asymptotic. And when we solve the quantum harmonic oscillator problem, we saw that we have to take the asymptotic limit, like x is equal to 0 or x is equal to minus, x is equal to plus infinity. At this kind of approximation we have to take, then we will get the um, hn alpha x. Okay, this polynomial, and from this polynomial we can calculate the energy and the wave function. Okay. Now, if we include something like x cube to take the asymptotic behavior, or x to the power 4, okay, at this place we cannot, maybe we cannot get any polynomial form. Okay, so for that case we also cannot solve it exactly. So for that reason we need another theory, so that we can calculate the contribution for this x cube or x to the power 4 or both of them. So to calculate this thing we need perturbation theory. So uh, these two are perturbation, that a new Hamiltonian that we added. Okay, another Hamiltonian, small Hamiltonian that you solved in your um, like semester 4 or 5, when you solve the quantum harmonic oscillator, that is the shifted harmonic oscillator. So you added E, E small e, and E is the electric field, and X you added this term with the normal Hamiltonian. Normal Hamiltonian was only this part. Okay, then you added the new term. So the total Hamiltonian becomes p square by twice m plus half m omega square x square plus small e. It will be minus or plus minus x. Okay, now what you did, you take this, for this term you make it a complex, you make a complete square, like x minus a square, something like that. So it is a shifted harmonic oscillator, and you solve it. So this new term, this is the perturbating term. Okay, this is the part of Hamiltonian that is new, that we are adding. Okay. And if we take the another example, like hydrogen atom problem, we like from the Bohr energy we get only the En, that is proportional to alpha square mc square by n square. Okay. There will be many term, maybe alpha is the fine structure constant. Okay. And in fifth semester, sixth semester, maybe you solve the relativistic correction or fine structure. In fine structure correction you did relativistic correction, Ellis coupling, that is the spin orbit correction, and the Darwin term. Okay, and Darwin term only contribute for the L is equal to 0, that means s orbit. Okay, so these three terms were the perturbation term. Okay, but at that time you are not introduced as a perturbation term. You are just introduced. It is the correction that we need. Okay. Now, if we talk about this relatively small thing, if we take an example, um, can you say any other correction that you did in your previous semester, except these three? You did any many other problems correction in your previous semester? Yes, as Sayonika said, that G-man effect, G-man effect, and JJ coupling. Okay, JJ coupling, like LS coupling, there is a JJ coupling. So these all are the perturbation term in the Hamiltonian. Now take a look about the relatively small thing. Okay, for the Bohr energy, this En that is the proportional to alpha square. Alpha is the fine structure constant, that is the V by C, and its value is 1 by 137. Okay. But for the relativistic correction in the kinetic energy, that was proportional to lambda to the power 4. Okay, for all of them, LS coupling and Darwin term also, all are these proportional to lambda to the power 4. So now if I take uh, delta ek by en, that is proportional to lambda square. Now if I do it 137 square, and if I just approximate 137 add just 100, then it will be 10 to the power minus 4. Okay, so you can see that delta ek, okay, is equal to or proportional to 10 to the power minus 4 en. Okay, so this delta ek, the part of Hamiltonian, the part of energy, okay, that is 10 to the power minus 4 times smaller than the en, that is the unpart of energy. Okay, so this delta ek, that is very very less than 1. In this case we can say this relativistic correction or LS coupling or Darwin term, this kind of thing, they are perturbation to the Hamiltonian. Okay, for any other case it can be 10 to the minus 5 or 10 to the minus 3 or many or more small, it will depend. Okay, uh, so this is the concept of the relatively small term, small perturbation, and in this way if it is very large, then we will not consider it as a perturbation term. Another problem that in the 1D potential box, okay, like if there is this is the 1D potential box, this Vx, this is the 0 within this portion, and it is infinity outside the box. Now if I introduce some this kind of step potential within the box, okay, or if I introduce Dirac delta potential, okay, Dirac delta potential at a position A, okay, 0 to L, and if I put at position A, if I introduce a Dirac delta potential, so what will be the modification in the energy, and what will be the modification in the wave function, okay, that we have to find. So if I summarize it, that we need the perturbation theory, because for all the time we cannot solve the Hamiltonian exactly. Okay, that's why we need perturbation theory, so that we can add some small term, in the small step we can add many energy term or many Hamiltonian, and we can correct our energy term, and we can correct our wave function is in small step. Okay, so we can classify this perturbation theory mainly in two part. The first part is time independent perturbation theory, that is written as TIPT in a small form, and on another is time dependent perturbation theory. Okay, so the problem that we solved till now, that Schrodinger equation H psi n is equal to E n psi n. This Hamiltonian H, they were time independent. Okay, they are not time dependent. Now, if we introduce the part of term that is also time independent, okay, then we will call it the time independent perturbation theory. Okay, like if I introduce a new term H prime to our system, like this relativistic LS coupling or something like that, then these all are the time independent. Okay, these all are time independent, so we will call it as time independent perturbation theory. If if we add any term, perturbation term, that is time dependent, okay, then we have to do the time independent perturbation theory. That thing is not in your syllabus. In your syllabus the time independent perturbation theory is there. So in time independent perturbation theory, we can again classify in two parts, that non-degenerate perturbation theory, where the energy for one energy eigenvalues, there is only one eigen function or eigenvector. But for the degenerate perturbation theory, like hydrogen atom problem or 3D potential box, uh, for one energy eigenvalue, there are multiple eigenvector or eigenstate. Okay, so we have to solve these two problems separately. First, we will start with non-degenerate perturbation theory. Okay, and to take some example, we'll take 1D potential box as our example. So this is the Schrodinger equation that we know till now. Okay, but I am talking that we'll introduce a new term. Okay, so that's why just to distinguish between them, what is the main Schrodinger equation that we will call as unpart of system, unpart of Hamiltonian, unpart of energy or unpart of state, eigenstate, and what will be the part of state or part of Hamiltonian. To distinguish between them, we will introduce our notation. Okay, so we'll introduce like this, as the Schrodinger equation has no part of term. Okay, that's why it is the we can say it is a zeroth order perturbation. That's why we no, we give a notation like in above it is the zero. Okay. We can all in Griffith you can just you will see that it is written like this. Okay, like this. So just not to confuse between the power, it seems like e to the power 0, that is 1. Okay, just distinguish between them. It is not the power, it is the order. As you are learning for the first time, that's why I am written in this form in the bracket. Okay, in the bracket 0, that that will say the what is the order of the perturbation. So the zeroth order perturbation, that is the simple Schrodinger equation. So here also we have to introduce 0, as En is the unpart of energy and the n0, this is the unpart of eigenstate, and these are the exact solution of H naught. We have to know En and the en0 and n0. Okay, exactly, we have to know everything about them, otherwise we cannot go for the perturbation. So this is the zeroth order perturbation. So for the 1D potential box, where this Vx is 0 from 0 to L, and infinity other portion of x. So for this, the wave function psi x, we till now we wrote it as psi n x. Okay, we didn't give the 0, but from now we have to give 0 to distinguish that it is the zeroth order eigenstate or the unpart of eigenstate. So this has the form of 2 by L sine of n pi x by L. Okay, and for the energy also, the energy is n square pi square h square by 2m L square. Okay. We know that n0 or psi n0, or you can say that psi n0, these both are same. We in this case, many times we will not write the explicit form of psi n. Okay, we'll just mm, give a notation as this. Okay, so it is very convenience to write. Okay, and as we know that h0n is equal to en0, and we know the value of en0, that is n square pi square h square by 2m L square. As we know that this value, and as we know the functional form of this psi. Okay, so we will not write this big term always. We'll just give the notation in this form, and if we work in the bracket notation, it is very easy to solve problems. Okay, so these functions, all the eigenfunctions for the 1D box, for n is equal to 1, 2, 3, 4 up to infinity, all these uh, eigenfunction or eigenstate, they are the basis state. They form a basis. Okay. So as they form a basis like I j k cap, x y z axis, so they form a basis, and from that basis I can generate any general state that you did in your last semesters. That if I want to generate a general state psi, then I have to take the linear superposition of psi n zeros. Okay, psi n zeros. Here also I can give the zero notation. So in this way we can generate any general state. So that's why we call that this n, all the n's, all the eigenstate, they form a basis. They form a basis. Okay. Basis of space. They form a space in where we can expand any state as a linear superposition of basis states. Okay, so this H0, this is the unpart of Hamiltonian. Okay, unpart of Hamiltonian. Now, what we want to do? We want to introduce a perturbation term that we will denote by H prime X or H prime R or R vector. It will depends on system. Okay. In the 1D box problem, this H prime X, the perturbation term that looks like something like this. Okay, that has some form that will be given. That will be given to you. So now, if I want to write the total Hamiltonian, so what I have to do? I have to add the unpart of Hamiltonian and the part of Hamiltonian, both. Okay, so that will give me the total Hamiltonian for the system. Okay. Now I can write this Hamiltonian in the form of H is equal to, H is the total Hamiltonian, is equal to H 0 plus lambda H prime X. Why I am introducing a lambda term? This lambda, that is the, that is a unitless quantity. Okay, and its value belongs to 0 to 1. It can take any value from 0 to 1. It can take any continuous value, 0 0.1, 0 0.2, 10 to the power minus 4 5, 4 into 10 to the power minus 5, any value. It can take any value, but it should be between 0 to 1. So it includes 0 and 1. So what is the benefit to introduce lambda? So if we tune the value of lambda, then we can tune the strength of the perturbation. Okay. So if we take small value of lambda, then the strength of this total term, the perturbation term, that will be small. So to modify the strength, uh, we can use lambda. Okay. And another thing, that this power of lambda, this lambda 1, lambda to the power 1, this power of lambda, that gives us freedom to track the order of the perturbation, whether it is the first order perturbation or the second order perturbation. That is that we can track easily by the lambda. Okay. And another useful thing, that when lambda is equal to 0, then this h, that boils down to h naught, that is the unpart of Hamiltonian. And when lambda is equal to 1, that then we get back this h, this equation, h is equal to h naught plus h prime x. Okay. So at that time, when lambda is equal to 1, then the contribution of the Hamiltonian, part of Hamiltonian, it has the full contribution. So by putting lambda is equal to 0 and 1, we can turn on, we can turn off and on of the part of Hamiltonian. For that reason, we introduce this lambda. And when you will solve the problem and we will develop the theory, you will see this lambda has a crucial role to develop the theory. Okay. And another thing, like as I said, that we can tune uh, the strength of the perturbation. So as we tune the value of the perturbation, so according to that, the value of the modified energy, that should also change. So that is given in this it is just a pictorial value, pictorial picture. So here I take a non-degenerate perturbation theory, sorry, non-degenerate perturbation example like hydrogen atom system. So there is only one state, then two, then three, something like that. There is the three-fold degeneracy, two-fold degeneracy, and the ground state had no degeneracy. So as we increase the value of lambda, okay, so this energy value also change. Okay. For lambda is equal to 0, the energy value has the En0, that is the unperturbed energy. When the lambda has value of 1, then we'll get back the full H, and we'll get the total energy, that total contribution from the energy, the total corrected energy will get back. Okay. So I will come this part later. So this is our total Hamiltonian. Okay. And now to solve the total Hamiltonian, and yes, so for the total total Hamiltonian or Hamiltonian, we'll use the H. For the total energy, we'll use En. For total wave function, we'll use N. Just N. No notation. No 0, no 1. So this will represent the total thing. Okay. So here we this is the eigenvalue equation. This Hn is equal to En and n ket. Okay, this is the eigenvalue equation that we also saw for the Schrodinger equation. This is also a Schrodinger equation, of course. So n is the eigenfunction of H, and En is the eigenvalue of the H for the nth state. So you may ask the question that why you didn't write like En0 or something else. Okay, why didn't use this N0 things, as we have the basis of N0s. Okay, the main reason is that this H naught, H0 and H prime, okay, if H naught and H prime do not commute, if they do not commute, then N0, it will is not a eigenfunction of H prime, and as these n zeros, they are not the eigenvalues of H prime, then this n zeros are not also eigenfunction of the total Hamiltonian. N zeros are eigenfunction of H naught, that is fine, but as n zeros are not eigenfunction of H prime, so that's why for the total n zeros, they are not the eigenfunction for the total Hamiltonian. That's why we have to take we will assume that there is a eigenfunction in that eigenfunction for the H. Okay. So this is the same thing, that Hn is equal to En, and En is the total energy, and n ket, this is the eigenvector or eigenfunction for the Hamiltonian, total Hamiltonian H. Okay. Now what we will do, after introducing this H prime term, this En, okay, should be modified. It will not be equal to En0. There will be some delta E. Okay. So this will be delta E. So to find this delta E, as I said that it is not easy to find this energy or eigenfunction directly by the analytic form. Okay, we have to add some small term. Okay, so maybe first delta E, or A into epsilon plus B into uh, epsilon maybe 1, C into epsilon 3, and maybe epsilon greater than epsilon 1 greater than epsilon 3. So the correction term, they will be smaller as we go for the higher order correction. Okay, it will be better epsilon 1 epsilon 2 and epsilon 3. Okay, this is the first order correction, this is the second order correction, and this is the third order correction, and this is the zeroth order. Okay, so as we will go to the higher order, then the contribution will come small. So you can visualize this thing as the Taylor expansion. So if a function fx, if we want to do the Taylor expansion, then what we have to do, and I am doing at x is equal to 0. So we have to take x f of 0 plus f of prime first order derivative at x equal to 0 plus f double prime 0 x square by 2 factorial f prime 3 0 3 factorial x cube plus dot dot dot. So what we are doing? We are doing we are adding the contribution from the higher order term small in a small amount. Okay. So in this way we are forming the functional form of fx. Okay. So uh, if we write in a compact form, that f to the power n by n factorial x to the power n is equal to 0 to infinity. Okay. So we are so as we add many small term, okay, in small step for develop this effects by the Taylor expansion, this concept also bring here. Okay, so to get the en, what we will do, we will expand this en as a power series of lambda. Okay, en 0 plus, so you can think it as lambda to the power 0, as lambda to the power 0 is 1, then lambda to the power 1 en 1 plus lambda square en 2 plus dot 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 maybe lambda to the power m en. Okay, so here if I write only en2, maybe it looks like e square. Okay, that's why I put this bracket, first bracket. Okay, so how to read this thing? enm, this thing, this is the mth order perturbation, and en, this is the nth energy level. Okay, and this whole term will be called at mth order correction to the energy. Okay. So in this way we can expand en as a power series of lambda. Okay, as we expand our Hamiltonian, like h is equal to h naught plus lambda h prime, we can also do that with the energy. Okay, so this is the main big contribution. Then this time will be smaller than en0, and this time will be again smaller than the en1 or the whole term. As lambda it is smaller than 1, then lambda square and lambda cube, that will be also small. Okay, so to do this perturbation theory, we always add step by step. Okay, small in a small step. That's why we expand en as a series expansion, power series expansion of lambda. Okay, this is the expansion of en. We can also expand our wave function n in the similar way. Lambda 0 psi n 0, this is the unperturbed term, then lambda 1 n1. Okay, so this 0 I am putting inside the broad notation, then lambda square n2 dot 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 lambda to the power n m n. This goes as the same the reading notation is the same. Okay, so n m, it will be called as mth order correction to the wave function. Okay, so now what we will do, this is our equation 1. Okay, here also you can put this lambda 0 as lambda 0 is equal to 1. Okay, this is our equation number 2 and this is our equation number 3. Okay, now put equation number 2 and equation number 3 in equation 1. Okay, now let's put it. Lambda 0 is 0 plus lambda h prime into lambda 0 n0 plus lambda 1 n1 lambda square into plus dot dot dot, that is equal to lambda 0. Now I'm expanding en e0 plus lambda to the power 1 en1 lambda square en second order correction dot 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 into this whole term in lambda 0 n0 plus lambda 1 n1 plus lambda square n2 plus dot dot. There are many terms. Okay, now what we have to do, we have to, of course we have to multiply this whole thing with the individual term of these n's. Okay, and this term also. And for here also, for both of in the both side we have to write the explicit form. We have to do the multiplication. Okay, so now what we will do, we will equate the uh, coefficient of the same power of the lambda. Okay, like lambda to the power 0. Okay, at first what we will do, we will equate the coefficient of lambda to the power 0 in the both side. Okay, before that let's write some term explicitly. Okay, lambda 0 is 0 lambda 0 in 0 plus lambda 0 is 0 uh, into lambda 1 in 1 plus lambda 0 is 0 lambda square in 2 plus lambda h prime. This is the h prime, lambda 0 in 0 plus lambda h prime lambda in 1 plus lambda to lambda h prime lambda square in 2. Okay, that is equal to lambda 0 plus there is many term en 0 lambda 0 n0 plus lambda 0 en0 lambda 1 n1 plus uh, lambda 0 en0, this will be lambda 1 lambda square n2 plus lambda 1 en1, that will be multiplied with the individual terms lambda 0 n0 plus lambda prime en1 lambda 1, sorry this is not prime, this is 1 lambda 1 in 1. Okay, and yep, and another term I want to write that will be useful in our next calculation. uh, of course there will be many term with lambda 1. Okay, and lambda 2 en2, lambda 0 n0. Okay, of course there will be like with lambda 0 e0 there will be many term. Okay, like higher order term of the lambda 3. Okay, same for the lambda 1 and other term. Okay, lambda 1 is 0, there should be also many term order of uh, 1. Okay, lambda square and other term that is left. Okay, so this is the explicit form we get. Okay, now what we will do, we will equate in the both side of the equation, we will equate the coefficient of lambda naught. Okay, lambda to the power 0, that is 1. Okay, here you can see, so this is the lambda 0, that is the lambda 0. Okay, that is the 1 lambda 0. Okay, here lambda 0 and lambda to the power 1, so that will give me lambda to the power 1. Okay, here what it will give me, it will lambda 0 lambda 2, the power that will be added, so that will be lambda square. Here also it will be give me lambda to the power 1. Okay, here it will give me lambda square. Here it will give me lambda to the power cube. Here it will be just lambda naught. Here it will be lambda to the power 1. Here it will be lambda square. Here it will be lambda to the power 1. And here it will be lambda square. Okay, so first what we will do, we will equate the coefficient of lambda naught or lambda to the power 0, that is h naught in 0. So from the left hand side only this term is has this has the contribution. From the right hand side of the equation there is one contribution, one, yeah, that is the one contribution, that is the en0 and the n0. Can you recognize this one? This is the Schrodinger equation. Okay, that is the Schrodinger equation. That's why I told at that time that this is the where, yeah, where it is, yeah, here. That's why I use the zero notation here, and I talk that this is the unperturbed or zeroth order, zeroth order perturbation. Okay, so this is the Schrodinger equation that we can solve exactly. Okay, and now if we equate the coefficient of lambda to the power 1. Okay, now we have to look for the lambda to the power 1. Okay, so from the left hand side this is the one contribution. Okay, h naught in 1, and there is another contribution, this is this one. Okay, h prime in 0. Okay, let's find out from the right hand side, this is one contribution, e in 0 in 1 plus any other term, yeah, this term e in 1 in 0, and there is no other term that can contribute. Okay, so this is another equation that we get by equating the uh, coefficient of lambda to the power 1. Okay, that is our first order, uh, so lambda to the power 1. So here sorry, here you can see that lambda to the power 0, that is the zeroth order Hamiltonian, and this is the first order correction in the wave function. Okay, So now if I add the order of these two, this is the zeroth order, this is the first order. Now if I add 0 plus 1, what is giving me? That is the 1. Okay, and here also this is the first order correction or first order contribution to the Hamiltonian, and this is the zeroth order in the wave function. So that is also, if I add, this is also 1. Here also you can see this is the zeroth order energy, plus this is the first order correction in the wave function, that is also 1. Okay, here also first order correction in the energy, order is 1, and here it's order 0, that is equal to 1. So this 1, this order of the Hamiltonian and order of the wave function, or order of the energy eigenvalue and order of the wave function, if we add these two order, that matches exactly with the power of lambda. Listen carefully, power of lambda and order of Hamiltonian and the wave function, or the energy eigenvalue and the wave function. Okay, this is the order. So if we add these two order, okay, that will should match exactly with the or power of the lambda. Okay, sum of order of h and n, or en and psi n. I'm not writing that thing. Okay, order, like this, sum of the order of this thing matches with power of lambda. Okay, power of lambda. So from this analogy we can say easily, easily that what is the coefficient, if we now compare the coefficient of lambda square in the both side, what we will get. Okay, from this argument we can say. Okay, so let's try with them. From the, for the age 0, it should come n2. Okay, for h prime it should come n1. Okay, and as there is no in Hamiltonian, there is only lambda 0, h 0. In lambda 1, h prime. Okay, so as there is no lambda square term, so there will be no term from, like if it say it is lambda double prime, so there is, as there is no term, if there is a term like this, so it should be lambda double prime x into n0. Okay, but as there is no term like that, so there will be no contribution from the n0. Okay, so it is not there. That should be equal with en. If I write 0, then I should write en2. Okay, plus en1, then n1, plus en2, then it should come n0. Okay, now we can match with the expansion that we did. Okay, this is our expansion. So yeah, so you can see this term is the first term, this is the our second term, this is the left hand side, and on the right hand side this is this one first term, this is the second term. Okay, and this is the third term, and there will be no other term, no other coefficient for the lambda square. Okay, so in this way you can write the coefficient of lambda easily. Okay, if you just recognize the pattern. Okay, these are the main another two equation. I 3, and now it is the fourth equation and the fifth equation. Now we have to find, let's see that we know h naught. Okay, we know psi naught, we know en naught. Okay, and h prime also we know. So what we don't know, we don't know n1 and en1, first order correction to the energy and the first order correction to the wave function. And also we don't know the second order correction in the wave function and second order correction in the energy. We will not go for the second order correction in the wave function. We'll just stick with the first order correction. So these three things we have to find now. Okay, so can you suggest any method so that I can find out, I can find out this en1. Now we have to find this en1. How can I find it? It is a constant, of course. So how can I extract this en1? Yes, Samika, right, that we just if we multiply with this equation both side. Okay, let's do here equation 4. Now if we multiply by the bra of n0, okay, then we can extract en1. Okay, multiply both side. Okay, so what we will get n0 h naught n1, okay, plus n0 h prime n naught is equal to en0, as en0 as a constant, so we can write n0 n1. Okay, and again as en1 it is a constant term, so we can write en0 and n0 inner product. Okay, so let's come to the first term. Okay, so it is n0 h naught n1. Okay, as we don't know, I can give the this sign or not, it does not matter. As we don't know n1, so we also don't know how h0 will act on n1. Okay, so we cannot perform this algebra, or we cannot operate h on n1 as we don't know the form of the n1. That's why what we will do, let's see, I write in this way or not? H naught n naught into a naught. Can I write in this way? See this, n0 is equal to en0 n0. Okay, now if I take the complex conjugate, what it will be? n0 a0 is equal to en0 n0. As the Hamiltonian is a Hermitian operator, it will act on the bra and on the cat and on the bra similar way, in a similar way. Okay, so that's why I can take this h naught with the n0. Okay, and as we know what is the value of this, we can perform the operation. Okay, so it will give me it will give me en0 and en0 n0 n1. Okay, so now write en0 n0 n1 plus n0 h prime 0 is equal to E n0 n0 n1 plus En1. Okay, as this is the inner product, and as they are normalized, that's why this is the this value, this value is 1. Okay, so this is En1. Okay, and you can see that this term and this term is the similar, so they will be cancelled out. Okay, so now we get the form of the E1. This is the N0 H prime N. This is a very simple equation. Okay, in the simple operation, we can get the first order correction to the nth eigenvalue. Look here, this H prime is known. Okay, N0, this is also known. That's why I said that we should know the En0 and N0 of the unperturbed Hamiltonian properly. Otherwise, we cannot solve it. If we don't have the information of N0, then we cannot perform this operation. Okay, and then we cannot also calculate the first order correction to the energy. Okay, that's why we should know N0. Okay, zeroth order eigen functions. So this is the first order correction to the energy. Okay, and then what we will do? Oh, of course, we can also we will do the first order correction to the wave function. Before that, let's do a example. Okay, so how this operation work out? Okay, so let's take an example, the 1D box. Okay, for the unperturbed system, what is the Hamiltonian? Each node is equal to p square by twice m plus Vx. Okay, x Vx 0 to L. Okay, and here Vx is equal to 0 for x 0 to L, and it is infinity otherwise. Okay, now add the perturbation H prime. Okay, uh, H prime, that is that V naught L Dirac delta L x minus L by 2. What is that? At the L by 2 position, if we introduce a Dirac delta potential, and the strength is given by V naught L. Okay, this is the strength of the potential. It like, don't assume that as Dirac delta, as we assume that it is the infinity at this point, otherwise it is 0. It is not true. Okay, uh, what is the true? That minus infinity to plus infinity Dirac delta x, that should be 1. Okay, so this area under the Dirac delta function, that should be 1. Okay, if this gives me area under the curve as 1, it will also can be a Dirac delta. But now if I do in this way, okay, so what I did, I stretch in one dimension, in the y dimension. I stretched the potential, and I shrink the in the x direction. Okay, so that it gives me the integration area under the value 1. Okay, so in this way we construct the Dirac delta function. Okay, and the strength of the potential is V naught L. So why it is L? Because, like, here you can see, if I don't put L, okay, then it will not match with the dimension of the energy. Okay. So dimension of the Dirac delta, from here you can see it is the 1 by L. Okay, as dx is has the dimension L, so to get the dimensionless quantity, Dirac delta has a dimension 1 by L for the one dimension. For the three dimension, it will be 1 by L cube. So as so this, the H without L, it has the dimension of joule per meter. Okay, so that's why I am introducing L. And why L? Why I didn't introduce any other length A or L by 2 or anything? Because like as L is the length scale of the system. Okay, this is the length scale of the system. That's why I introduce L. Okay. So now what we have to do? We have to calculate the En1. Okay. So that is what? That is the N0. Okay. And another thing I forgot to mention, that this is the first order correction. Okay. And this En1, this is the first order correction to the nth eigenstate or nth eigenvalue. This is the, if you see the right hand side, this is the expectation value of the part of Hamiltonian in the unperturbed basis. As this N0, this is the unperturbed wave function. Okay, unperturbed basis. Okay, and as we are, what this means, this is the expectation value of the part of Hamiltonian. Okay, that's why it is called that the first order correction of the energy is same as the expectation value of the perturbation Hamiltonian in the unperturbed basis. Okay, so for the En, we have to take the expectation value of the perturbation Hamiltonian with the nth same states, zeroth unperturbed state of the same state, not the other state. Okay, so that's why it is very easy to calculate the En1. Okay, so when we will see the correction of the in first order correction, we'll see that if we don't know the E1, we cannot calculate this one. Okay, so to calculate the En1, we don't know, we have to know only N0 and the H prime. No other requirement is there. Okay, but for to do the N1, we have to know the N0, En0 and En1. Okay, these three are needed. That's why first we have to calculate this one. Now let's do it. Is H prime and N0. Okay. Now I want to convert it as the in a in a position space. Okay. So psi N0 is complex conjugate H prime psi N0 into dx, and the limit will go to 0 to L. Okay, here many of you can do a mistake. Okay, so what you can do, you can do 0 to L mod psi 0 square H prime into dx. In general these two are not the same, because if H prime has any differential form, del x or del 2 del x square or anything, if it has any differential form, so as you saw for the relativistic correction, that was the p to the power 4. Okay, this kind of correction, if it is there, then these two terms are not the same, because first there will be a derivative, then it will be multiplied with the size term. So don't do this thing. Okay, don't do this thing. This is the wrong. These two are not the same in general. Okay, so now en1 that is equal to 0 to L. Now if I write that psi n0, that is equal to a of sine of n pi x by l. Okay, so it will be a star sine of n pi x by l. H prime is v naught l Dirac delta x minus l by 2 into a sine of n pi x by l into dx. Okay, so it will be 0 to l mod a square v naught l sine square n pi x by l Dirac delta of ax minus l by 2 dx. So this term will come out. So a square is equal to uh, 2 by l into v naught l 0 to l sine square n pi x by l Dirac delta of x minus 2 into en 1. Okay, so now this ll will be cancelled out. Okay, so this will be this is the Dirac integration of the Dirac delta function. This will give me 2 v naught sine square n pi x by l. Okay, en1. Okay, now find out for different n what is the value of en1. Okay, for n is equal to 1 e1 1, if I put n is equal to, oh sorry, it will be l by 2, that is equal to 2 v naught sine square n pi by 2. So here in place of x, l by 2 will be l by 2 will replace x. Okay, so if I put n is equal to 1, there will be sine square pi by 2, that is 1. So it will be 2 v naught. For n is equal to 2, for the first order energy correction for the second energy state. Okay, e2 1. So if I put n is equal to 2, then is equal to sine square pi, that is sine square pi, that is 0. For n is equal to 3, can you tell me what will be the result? So Sayamika is saying that 2 v naught minus 2 v naught. But for n is equal to 3, so sine square 3 pi by 2, that is equal to like sine square pi plus pi by 2. Okay, as there is a square, so there will be no minus, it will be plus 2 v naught. For n is equal to 4, e4 1, that is 0. For n is equal to 5, e5 1, that is equal to 2 v naught. Okay, for n is equal to 6, it is again e6 1, it is 0. So what we can see, for the odd n, for the odd eigenvalues, eigenstate, there is a contribution, that is 2 v naught, and for the even state, the energy eigenstate, they are not changed. Okay, they are same as it is. Okay, so they are unchanged. Only the for the odd eigenvalues, en1 is equal to 2 v naught for odd n, where n is equal to 1 3 and 5, and that is 0 for even n. Okay, n is equal to 0, sorry, not 0, 2 4 6. Okay, so we got the value of the first order correction of the energy. Okay, now let's try to write the full energy. Okay, en 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 is equal to what? En0 plus lambda en1 plus lambda square en2 plus dot. Okay, so at first we'll only calculate up to first second order. Okay, So we will truncate all the other terms. Okay, and here what we will do, uh, we will put lambda is equal to 1. Okay, so why lambda is equal to 1? As we are considering, if we consider our Hamiltonian, for take lambda is equal to 1, that is simple, h naught plus h prime. Okay, so what we calculated, this thing this is the contribution from the whole age. Okay, whole Porter Hamiltonian. Okay, this is the full contribution that we calculate. Okay. Now if we put lambda is equal to 1, then we will also get the corrected energy for the full contribution of age. Okay, so En becomes En0 plus En1 plus En2. Okay, this is the energy we have, we will get. Okay, so for e1 en0, that is equal to h cut square pi square by twice m l square. Let's put it as um, epsilon. Okay, so this is the epsilon plus for the en1, that is the 2 v naught plus en2, that we didn't calculate till now. Okay, we'll calculate later. For the e2, that will be the n square, that is the 4 epsilon. Okay, and there is no contribution for the from the first order of the first order correction to the energy. We don't know whether second order correction will be there or not. For the E3, so I am showing how to write the full energy. Okay. E3 is the 3 square, that's 9 epsilon plus 2 V naught. Sorry, this will be 1 1 plus E3 second order correction. For the E4, it will be 16 epsilon plus 0 plus, so it will be 2, as n is equal to 2. E4, E2. So in this way it will go. Okay, so the second order correction we didn't calculate it yet. If we get any second order contribution, then we have to add. Okay, and we will get the total energy for the for this Dirac delta potential at x is equal to L by 2. Okay, of course these all are the approximate approximate energy, because we didn't take the higher order term. But we'll see that this is the 2 v naught, and when we'll calculate the e12, we'll see that that will be very less. It will be less than 2 v naught. Okay, so from that we can at least observe that the higher order term will also be small. That's why we can neglect that thing. Okay. So this is the one example that we did. Okay, let's see. We'll do the correction in the wave function for the first order correction in the next class. Okay, so in next class what we will do, we will do the second order correction and the first order correction in the wave function. First we will do this, then we will go to this step. Okay, but before up to next class, of course you have to revise this thing from the Griffith and from the Sakurai. Uh, you also have to revise 1D, 1D, 2D, or 3D potential box, uh, 1, 1D, 1D simply harmonic oscillator problem. Okay, in the operator form. In the operator form is A data. This is the lowering and rising operator, okay. So like if I do m a square n, okay, then what I have to do, m, it will be like this, okay. So first we have to calculate this one. So m a dagger root over of n minus 1, that is equal, again a will act on n minus 1, that is n minus 1 m n minus 1, and n minus 1, and this thing that will be conical delta m n minus 1, okay. So this expectation value, this will be valid if I take like m is equal to 1 and n is equal to uh, 2, okay. Then this expectation value of a square, a operator square, that will give me non-zero value, because like if I want to calculate x's cube, okay, then what I have to do, I have to convert x, we know x is equal to, I think 1 by something, it is proportional to a plus a dagger, okay. So we have to replace x by this term, okay, and we have to do a plus a dagger, a plus a dagger, a plus a dagger, okay. And then we have to operate from this side, okay. So do revise all this thing, okay, because when I'll do the any problem, it will be a time taking to revise all this thing. Yeah. Do these problems uh, carefully. And another thing, hydrogen atom problem, okay. Just see the solution, and psi 100, psi 210, side to 1 plus minus 1. Just remember these three wave function. This is enough for the calculation. Hydrogen atom problem will come later, but this two thing, potential oil and the simple harmonic oscillator, these two thing, whatever you did in your till your last semester, you should revise all the things, okay. So if you any query, you can mail me or you can message me on WhatsApp, and any if you have any comment, how can we improve this course, what we should cover, okay, what is your expectation, you can tell us, we can introduce that thing, okay. So see you in the next Sunday, okay.